Good morning. All right, hey, we're here for day 2 of the conference now. My name is Tom Andriola. I'm the Vice President and Chief Information Officer at the University of California System, and also one of the co-chairs of the CENIC Board of Directors. I want to welcome you to day 2. We've got an exciting lineup today, and I'm here to introduce our morning keynote speaker. But I'd like to start off really talking about the CENIC network, and we all love the CENIC network and what it does for us. And my background in technology and a lot of the work I've done in healthcare has really been how do we leverage data in healthcare to drive better outcomes with our patients. And the CENIC has been a huge part of what we've been able to do and push the boundaries in health, and we're really looking forward to how we'll continue to push those boundaries. But if you look at the present day, our lives in any field of business is more and more being shaped by the collection of data, the meaningful use of data, our ability to visualize that in impactful ways and share it with others for the forms of messages. And we are increasingly more connected to these data sources, whether they be things that we collect at our universities, at our libraries, at the different types of institutes and museums. And we're really unprecedented in our ability to use the infrastructure that we have available to us to improve our scientific and analytical capabilities. A lot of new interests and new areas, the field of data science have emerged, and the response to that has allowed us to use the CENIC network to drive those advances, and many of our institutions are at the forefront of that. But if we look to the future and the potential that we have, the state-of-the-art presents challenges that come with many, many opportunities. They not only push for new innovative capabilities in composing data management and use of analytical methods. They can run anytime, they can run anywhere, they can do it at increasing speeds and data throughputs. But as we've talked about here at CENIC, it's not just about the network, the physical network, but we also need to develop the human network because we often lack the collaborative culture and effective methodologies to translate these new methods into real value that impact people. And so we have to look at the people culture aspect, the people network aspect of this at all. And so for the future, a collaborative network world, we like to call it, is part of a data science process. Any solution architecture for data science today depends on effectively using multidisciplinary data science teams that have both humans as well as technology involved in them. The talk you'll hear this morning provides an overview of some of the recent work that we have at the University of California on networked application architectures for dynamic data-driven wildfire modeling and smart cities. It will also explain how focusing on some aspects of the planning phases in data science and creating measurable process that spans multiple perspectives and success criteria. Lastly, we'll introduce a model, something we call the PPODS methodology, and a family of composable tools for team-based data science management process. So with that today, I want to introduce our keynote speaker today. Dr. Ilkay Altintas, who is the Chief Data Science Officer at the San Diego Supercomputer Center at the University of California at San Diego, where she leads the strategic coordination of all computational data science activities while overseeing application-based solutions and their related technologies. Dr. Altintas also leads the Cyber Infrastructure Research, Education, and Development Division, better known as CIRED. CIRED encompasses about 85 researchers involved in a vast variety of projects such as bioinformatics, computational chemistry, geophysics, oceanography, 3D modeling, analysis statistics, visualization, and many, many more. How she gets any sleep, I have no idea. In addition, she serves as a principal investigator for something called the WhyFire project, which is a program that supports an integrated system for wildfire monitoring and analysis of cyber infrastructure that is existing in support of public safety organizations across the state and disaster preparedness. Without further ado, I'd like to bring up Dr. Ilkay Altintas.
Good morning. It's an honor to be here. Thanks for inviting me. And nice to see the room full. So I come to this from a user's perspective. I use the networks. I use the networks for science and society and education applications in different formats. So when I went about creating my talk, I really tried to bring this forward. Hope this is going to come across in the end. But really, when you think about it, what's the network useful for? What do we use it for? And who uses and what it does for its users? It's first about making connections, right? It connects people and communities, data and applications, people to information, or people and information and services. And in many of our recent examples, it connects learners from around the world to classes with these massive online courses. But I think the biggest one is whenever you have an idea and you want to make it available to the masses, you go to a network. And those masses could be education-related masses, like we are talking about here, research-related masses, or it could be the public. And I think recent applications of network is really connecting all these different parts of the networked world, and the lines and boundaries are really thinning. What we do for research suddenly becomes available to public as a societal application that builds on scientific models and impact. So we are really changing the world through these networks, and I think people in this room have a lot to be proud of in this space. So on top of that, I think network is really used for communication and collaboration while we get to these. So any application that we build and any technology that we build on top of these networks, it should be built around these concepts. So, and one of those applications and technologies, or a set of those, are related to data sciences. So I'll sort of share my views on how do we do data science in a networked world, or in a world that's becoming increasingly networked. It's becoming highly networked at different speeds. But just to take a step back to simplify what I'll talk about, what is data science? Right? The word on the street is we get big data and then turn that into something that we call insight. And based on that insight, we can take actions. Right? So that would be everything we talk about: precision applications, smart applications, data-driven applications, evidence-based applications. There are all these different words that define this exact thing. But when you look at it, we go from big data to insight, which is itself a data product, so it becomes part of the knowledge base. And we make it a part of the big data. So it's very dynamic. It's constantly iterating. It's constantly contributing to what we know about ourselves, our society, our world, our environment, our universe. And through the data, we are sometimes asking questions. Sometimes we know what we are looking for, go for that data to bring it in and turn it into hypotheses and do analysis and modeling on that. Let's say a bookseller's application, they go to historical data. They first look at customer demographics, book reviews, and anything they can basically get about a customer to identify what kind of a book this customer would like, so they can have a recommendation on that. And then when you combine that insight, which is itself a data product, with new book information, you can now go to another thing. It's called maybe who is likely to like this product. So it's a combined insight. It's not just one insight. It's a bunch of data products coming together through curating data over time. And then the action you can take on this is how can we market this book to the right audience. And go from what we learned to something that we can benefit from as a business in this case. And to market it to the right audience, also we need to know a little bit more about the customer. So there's another insight that we need to drive on there, because what kind of marketing would work for this one customer? So there are multiple things that we learn coming together to create a combined impact in the situation. And in many other cases, it's the same. We have historical data, we have near real-time data, and near real-time data we collect from the network or different types of networks, and we turn them into predictions that we can use to help in different contexts. Did we not do that? We did. Although it's not always the right prediction, we have better predictions. And based on that, we take action. We take an umbrella if it's going to rain or things like that. So why are we talking about it now? Why is the increased interest in data science? I think there's something about the data. We call it big data. Big data is defined by some V's. If the data comes at certain volumes, at various rates, and with different types of schemas and complexities, it is called big data. So it doesn't even have to have large volumes. Lots of small data coming together can be big data, or something that has the challenges in different V's of big data that I was alluding to, like volume, variety, velocity, defines big data itself. And then we have the now means to compute on this data anytime, anywhere. So the combination is actually both a challenge and an opportunity. In some ways, it's called a Chopper Trinity. So because they enable some things. They enable what we call now dynamic data-driven applications. And some of which I listed in the bottom there. It starts with smart, personalized, precision, and things like that. That smart means there's a sensor out there, and we are getting the data from that measurement and using that to drive an application. Personalized means we are really targeting a specific person or an organization to help with the data. So there are different ways this is coming together, but the idea is, are we getting the data and serving it to applications in curated forms as fast as the applications need? And are we deriving the applications through the iterations of this process? And turns out it needs a lot of different expertise to create this environment. In data management, data-driven methods, scalable systems, resource optimization. When you have a lot of data, you need to really use it in the best way possible. But more importantly, human beings who can understand this process, human beings who have this skill. So I think that's what brought us to this new era of data science that we are really thinking, which is pushing a new discipline to emerge on top of the age-old statistics, math, cognitive science, and things like that. Everything that we learn about computing, how people learn, how systems learn, and how we can drive statistical conclusions from data, they're all coming together, but this time at a massive scale. And they're transforming everything in our lives. Let's say geospatial big data, any geoscience lab now. I actually went to an NSF-sponsored field trip with some geologists a couple of years ago. And, we were in the sun for hours, which I enjoyed massively. We took strike and dip. We looked at different rocks, and we drove the idea was to understand how they collected data. And I enjoyed the whole process, other than standing in the sun for hours at a time. But now, after that, I have a huge respect for the boutique data sets that, little spreadsheet that people put a month of work in that heat to create. So this was maybe most of the geoscience labs back when, but now we can combine that type of work with real-time sensors, imagery, satellites that are becoming more and more high resolution, and many other modern sensor technologies. And that creates, of course, a huge volume of data that doesn't fit in a single server in a lab. So we need to really do things through the network more and more. And it has a lot of variety in terms of images, time series, and relational data set like we did before. And the data comes in different speeds, different velocities that we need to adjust at times. Suddenly when a natural phenomenon happens, can we increase the frequency of the data and still make our applications fit that scenario? And through that, of course, the data comes at different uncertainties. When we use technology and not just depend on what we know, we need to identify that uncertainty before we can use that data in the context of an application. But the reward is big. It has a lot of value, and when we start combining these different data sets together, we can understand things that we didn't understand before in a different way or in new ways that wasn't possible before. Similarly, biomedical sciences, we have a similar transformation there. We had these big simulations that consumed a lot of the supercomputing resources. It was a very high-performance computing activity until last 2 decades. And with the introduction of new data collection methods like electron microscopes, now we have an opportunity to learn from the data we are collecting from these instruments and feed what we learned into simulations that we have. So that's, again, this data-driven simulations, and how do we steer the simulation based on what we know, what we measure, makes things a lot more doable and scalable to do further science with those. And this is not really a surprise to any of you, I'm sure, but over the 10 years, this decade we are in, we are expecting growth in data sets by a factor of 44. And it's the Zettabyte Space. And I really like this graphic, which I didn't make, that there is actually the Milky Way in the middle, because that's exactly what we see if we were to scale out 10 to the power 21 times into the universe. So, we are creating actually a Milky Way of data as we are speaking, everything we are collecting. So that really is a concept to sit on and think through, what we are doing and what's the opportunity here. And how do we amplify then the value out of this data? What I'm trying to actually depict here in this image is we have this massive data and now access to high-performance computing at scales that we didn't have before, in growing scales as we work on every day. How do we take those two and use it to sort of push the data up and bring it to what I call a high-value zone so others can benefit from that? And once you do that, maybe learning the images, biomedical imaging scenarios, for example, you can use both to distill biological entities and things like that in those data sets, that we can now use those for driving simulations or validating applications and things like that. That then expands also the communities that can use this data. Something maybe that I couldn't visualize on my mobile device, now that after I went through it and I reduced that data set to what's important about that data set, it becomes available to the masses through mobile devices, for instance. And it enables many different applications with the right context. You know what it is, and you know the uncertainties about that, and things like that. It's all a part of that high-value zone that enables other applications. And some of those applications can benefit the society. And how can we find the connections within those data sets and applications so we can actually improve the society as well as scientific research and education? To do that, we need to create an ecosystem that involves all of us. We need to work together, and that ecosystem is data-driven and scalable. and dynamic and process-driven, as I was using all these buzzwords until now, but it's also highly collaborative. And that collaboration needs some things. Everything on the right, actually, is needed to make a collaboration successful. We need to make this process accountable, reproducible, interactive, heterogeneous, so we can have different nodes of computing, data, networking, and applications. And it requires and includes different expertise coming together. How would that look like? To summarize everything I said until now, collaborative groups come together around data or around questions, and it goes through some machinery, with the hope in the end we'll have those connections, that HighValue Zone or dashboards that we can derive conclusions from or decisions on. And that machinery has data management, data analytics, computational sciences, especially in scientific disciplines, and advanced infrastructure in it. And something has to bring all those together to make this ecosystem impactful. So then what we are trying to do is amplifying the value of data related to something, X, and that should benefit Y. Like X to Y is a mathematical way of maybe looking at it. And that's related to anything. It's science, business, society, education. So something that we talked about yesterday, I apologize if it's a repeat for a few of you, is one thing was, what if that X was wildfires? What it benefits? And how do we do it in a collaborative, networked way? Because the data and some of the systems we build on are across a network, and we need, again, that teamwork, that collaborative expertise to build that. So the why here we picked for that application was because these wildfires are happening, and when they happen, no one knows where they are or where they are going. There are some inklings of it, of course, but in a data-driven, physics-driven way, how can we predict the rate of spread of fire, the direction of the fire for the next couple of hours, and feed it back to disaster response agencies at speeds that were unprecedented. So when we started, we said 15 minutes. Now we are down to 2 minutes. So that speed actually can change based on data availability and how we make use of the resources. So the NSF-funded WhyFire project was set out to do this a couple of years ago. It was about 2013 when we were funded, and a couple of years before that, we were doing definitely the prototyping and things like that for this. But it's to bring that big data from HPRN and satellites and many other data sources, and definitely still be able to monitor those data sets, but also visualize and do fire modeling on them. So closing that loop between the big data and the modeling and iterating on it in a way that we can inform the response agencies and others. And did we not have those before? We did, but these system integration in a dynamic way that makes use of these and curates every data set wasn't there. I want to see if we can play this movie. Should I let you know earlier, maybe? Excuse me. Can we turn on the sound, you think? I have the HDMI, or maybe I can share the movie link later with the group here. Maybe we can move in the interest of time. Okay, got it. So we built this infrastructure on top of what existed before. It was a network that inspired us in the back county of San Diego, the HP Ren Network. It was built by NSF support from 2000 on. And in the back county of San Diego, we have had high-resolution data about the weather. Mountaintop cameras were giving us views over the fires that are happening. And we had some way to bring that through this high-performance network into the applications at the speed in real time they were generated. And the Farsight tool was used also by fire agencies before, but the earliest they got a predictive model was a couple of hours into using the existing systems. It was a couple of hours into the fire, which is really not enough in terms of speed for Southern California or California fires, or in general wildfires. I think having the knowledge of where it's going to go the moment the fire happens really helps with the management of the fire, because they grow big in really short amounts of time. So what we did is not just integrating data and those models, but we wanted to go one step further. The fire is moving, and as we are getting more information of the perimeter of the fire front, can we now use that information and learn about the dynamics of the growth of the fire, what the fire is doing over time, and adjust the models based on that. So when you look at it, it actually would move over time. The models are not static models. They would get iterated, and we would learn more and more about the fire as it's happening. And we said we'll use many other investments by NSF and others in terms of workflows, networks, high-performance computing. It actually brought together all those different bits to come up with that rate of spread information and communicate that to what we call the fire map tool, which we'll demonstrate in one of the upcoming sessions. And when we started, data revolution, so to say, hasn't happened yet. So everyone that we were talking about this was, oh, you'll never get that data, right? It's just, and we just said, if we just raised eyebrows that this can be done, we'll be good. So we would go back to the historical data and generate these scenarios and show it. And at some point, when we started building these things, it started getting interest from people like the Los Angeles fire chief. And he said, what do you need? When he called me, I was trying to get a contract from NASA to fly helicopters over the Northern California fires at the time, so we have a data set to work with. And he was like, okay, I'll give you what you need. I'll just fly my helicopters whenever we have a fire, and you'll get that information. So suddenly it was becoming a reality, and them, by the way, being connected from their helicopters through radio connections or to be able to send us the data as they are acquiring was a big part of it as well. So then the system grew into an interface that whenever a fire started, you could bring and curate these data sets and create models of the fire spread for the next 6 hours. 6 hours was also given to us by our advisors, and half-an-hour blocks was also a result of a collaborative analysis of what's useful in terms of knowledge or insight for the firefighters. Come forward to 2017, over the really devastating fires of fall 2017 throughout California, we noticed public needed this information. They found our website, we didn't advertise, and we had 800,000 users, unique users, IP addresses, access our servers, and we had about 8 million and more hits over that time. The system was also operationalized as a part of a public-private partnership with the San Diego Fire Department and General Atomics. When the Lilac fire happened, the first time this system called SDAIRS was tested was the General Atomics aircraft that can give us really detailed IR measurements or sense data over the fire imagery went up, and every half an hour they would give us that perimeter information that we never had, and people said you'll never get. And we use that to adjust and really iterate on our approach and hone our approach to real-time data availability. And the outputs of the system, as you see the half an hour colored blocks here, was fed into the state's scout system to be combined with the rest of the information that the fire authorities are seeing and using. And if you look at this, it's hard to see, but there's a white line here. That's the actual fire perimeter. So we were pretty close, but in science, pretty close doesn't cut it. We are still doing that analysis of that. But the thing here is the model is being adjusted based on real-time information. So the more information we'll have, the better, more accurate certain information we have, the better these models will be over time. The same system was operationalized in Thomas Fire. And as you might know or might not have noticed, Santa Anas are the fire conditions in California, Southern California. And over Thomas Fire, we had 3 major Santa Ana events. So the fire started December 4th, December 10th was another one, December 17th was another one, and sometimes in December 17th, we were called to do more measurements. So it wasn't just the beginning of the fire, but now we were asked to model maybe the fire front in different places and see how, for example, a controlled backburn would affect the fire growth and things like that. So that was definitely a new usage of it. But what happened over the Thomas Fire is it spread like wildfire. It's the literal use of it. These are the satellite detections over the fire, and gray is 72 hours. But you see here, when I replay this, the first incident happens, and then there's a boom, second one, and then there's a third one. So being prepared and being able to understand what's going on in real time really helped here. So how do we bring the data together? Of course, get asked a lot. There's a lot of machine learning. We have different case studies. Every data set that we bring in, we try to curate it so we actually understand the uncertainties of the data. We understand resolution of the data and different things related to the imagery. What actually a location-specific Santa Ana event is. It's not actually homogeneous through different parts of different counties. Even doing natural language processing on radio communications is something we considered because firefighters actually discuss local information. Some of it is done, some of it hasn't been done yet in this list that we are working towards. The idea here is they all require dynamic and programmatic access to data, and they all require a periodic cycle to that. Everything we do has to be refreshed based on the data availability or the resolution. Or it should be ongoing. If it's a radio communication, it should be ongoing. One of the opportunities there, for example, is the classification of fields. Field databases are actually the weakest link in fire modeling because they are never accurate. At best, they are 2 years old, and we need to know a more detailed, we need to have a more detailed understanding of these fields and recent information on these fields to be able to do better modeling. So what we are doing is we are using imagery from high-resolution satellites in collaboration with Planet Labs and Digital Globe. And through some deep learning processes and clustering of those imagery, we think we can get a more accurate understanding of the fields on a periodic basis. You don't have to do it every day, but can you do it weekly? Can you fly a drone, very detailed drone over it, or capture satellite information and update the field databases so we know what's going on out there in the field when a potential fire starts? So it's a big effort. Of course, I'm not alone in it. I'm actually just a messenger to this work here. A lot of these people, if they can raise their hands, are in this room. If you'd like to talk to them. But what I want to point out too is that middle layer. You guys are important too, but so the students. How do we involve this many students? If you look at those number of students, they helped with a lot of it. And they helped with a lot of it in a very structured way. Our goal here was to create a process so we can involve them when we need them and let them work on what they work on to become part of that overall entity. So when you look at a data science process, very simplified, this is the process that a team does, right? Data acquisition, preparation, analysis, reporting, and how it can be a part of those actions is a big process. But there is these iterations in it, and each of those steps can have these 5 steps, by the way. Now, you can actually apply this process in hierarchical forms and combine workflows in different ways. And this is not something we only do for wildfires. We do it for drug discovery and molecular dynamics applications. This was funded by NIH and NVIDIA. There are 2 applications here, actually, to fit 2 slides in one. There is one related to what we call the guardian of the genome, the p53. If they are not activated, one of the hypotheses is cancer forms a lot easier. So this is the workflow on the side is related to p53 reactivation. And then the workflow, the Amber GPU tool on the right, is to create molecular dynamics that can be used in drug design process. So, and the benefits here is every step here can be built by a student. And by bringing together these different things that we get help of the students, we can create a big application. And we can compare methods, we can teach those different methods to students, and we can reuse some of the work that's been done. And hopefully the whole thing becomes reproducible because you keep the whole process and the data related to that process with its provenance. So we use workflows for that process integration. Now that machinery I was talking about in the beginning. How did we get here? We've done some earlier things that helped us to get here. This was in 2004. We followed a Scripps ship, Ravel, and we got imagery from the ship, and we looked at nice fishes. I loved demoing this, right? Every time I demonstrated the system, I would see something nice, or sometimes I wasn't lucky enough, I would see them dark because it was dark there. But the idea is we could actually, in 2004, stream some things from the ship out in the sea and observe some things. We didn't know how to process that in real time, but there was some things going on. And that was the same workflow application before its makeup transformation. It was the same tool that we were using. The architecture was the same. And Tobin Fricke is the student who also built this strain meter channels and signal processing on that using another real-time processing workflow for RoadNet, had worked on both applications. So, and that student is now a simulation engineer with a physics PhD. So they actually really pick up on this and move on. And another student, Nandita, we worked on. This is like WhyFire 2006. We have the workflows running in the background. The outputs were being communicated to a web interface on real-time data in real time. So we could do some things, but the technology and data revolution wasn't there yet. This was one of applications we were doing proof of concept case studies, which the ORB, the data interface to all these real-time data with Frank Vernon and others is still being useful, right, on networked applications. And Nandita, the student who worked on it, now is doing driverless car and looking at human aspects of it, collecting data about the people and their experiences in those driverless cars. So, that data bug they got, they really did great things with it, and we were able to train them and increase their understanding, hopefully, at that time. So my research group, which was scientific workflows from like about 10 years before 2014, got rebranded, or we rebranded it as workflows for data science, because we noticed data applications were different than purely scientific coordination applications. There was a lot of exploratory aspects to it. There were a lot of things that we used for the applications we worked on for drug design, as I mentioned, wildfires, or using big data approaches to sequence analysis and bioinformatics, like accessing, querying data, supporting computational analysis, reuse and reproducibility, standardizing and formalizing the process, and training the students. But that second bullet, supporting exploratory design and how we can take what we explored and make it scalable, wasn't a part of the scientific computing picture as it relates to computational data science. Right? There was definitely exploratory data science, and it's been used for a long time, but being able to integrate what was going on there with a scalable application needed more things to bridge that gap, like the WhyFire case. And we have expertise within the team for team building, process management, performance and provenance tracking, and training the students. But we always work with experts from different domains. Right? Application domains, modeling, integration, data management, people who build analytical methods and communication and visualization pieces into this whole end-to-end solution. And when you look at a data science team that needs to collaborate, they're all over the place. In science, there are scientists and engineers and methods experts, as I mentioned. But in business, it's not that different. There's the business managers and analysts who need to be a part of that group. And there's the big storytelling pieces. How do you communicate the results to policy, to public, and things like that? So this is what I do as a part of my daily job. I'm in a lot of meetings, and I try to understand what people are trying to do. And I often tell them, don't go into the details yet. We are not ready to hear that. And then I try to get them to speak, right? And focus on a question before we can get into the details. So I try to give them a sense of purpose so they can be motivated to understand each other. And this is also very inspired by what is called the lean method. You discuss ideas, code a little bit to prove that, and then put metrics on it, and constantly iterate on that process. So we go from the question to the data science process. I keep saying process, so maybe it's easy. It's good to give one little example. Acquiring means how do you get the data to your analytics. Preparation means how do you then explore with this data and make sure it fits for the analysis, and it's clean, and you know what this data set is about. And analysis is the typical machine learning, statistics, and other methods that we apply to data. Reporting would be presenting your findings, and ACT would be using them. Right? And that's the active part of the process. So when you look at that, first part is data engineering, and the second part is what I call computational data science. I'll always say computational data science because what I'm really interested in is how data science come together with the rest of it, the rest of the scalable computing, so we can actually iterate on those insights to drive scientific and societal knowledge. And that means there are many iterations there, and there's a scale in each of those. Even at the data acquisition, when the data is being collected at unprecedented rates, you need to think of doing something more scalable to collect the data. And when you look at it, it could be building, exploring, scaling. Each step we need to be able to report and take actions. We can't leave any of that behind. So you can look at the process in different ways. But to make things dynamic, the most important part of it is programmability. It needs to be programmatically doable. We don't have the luxury to sit down and, we need to do it, of course, at parts of it. But when we go to scalable applications, everything needs to be programmable. The interfaces between those steps need to be defined. And I'll go all to say data science or insights happen really in the boundary of each step. So we built a methodology that we call Process for the Practice of Data Science. How do we bring everything together and go from data to those products, and to make things programmable, scalable, and reproducible, and provide tools for being able to do that. And to go with the pea pods analogy, my students laugh at me because it's maybe too cutesy, but there are peas in pea pods. So people come around a problem or a purpose, and they create a process. That process needs to be scalable on platforms, and the whole thing needs to be programmable. Very simple to say, but it's hard to achieve at times. And when you make things programmable, can you put metrics on that with different concerns? It could be privacy, it could be speed, it could be performance, it could be accuracy. Can you actually decide on that at the boundaries? So you know when you created an insight, that's something you can trust. So you can actually put some probability on those results, so you can use it in the actions as much as you want or as much as you trust. So here, each step we define, which is a pod, as a sub-process, and it has its own purpose, stakeholders within the team, expectations are defined, metrics from performance, economic, accuracy, policy, privacy, reproducibility, and political, and many other perspectives are defined. And we know then about each step, what are the knowns, what are the unknowns. Then those metrics that relate to cost, timeline, and everything I mentioned before can be used to judge how well we are doing. To zoom into a different example, just the first two steps can have different interactions between people doing these different boxes in the bottom, right? Data exploration, schema integration, query processing. These are all parts of data preparation and analysis at times, so the boundaries are also not that clear at times. And it goes into, let's say, machine learning, but they need to constantly, all those boxes have to inform each other and have to tell each other some things programmatically before we can integrate them. So we create those solution architectures. In the past, as I've shown examples from 2004 to 2006, it was data management and storage, data integration and processing on top of that, and then coordination and management of the workflow was on top of that. Now it kind of looks like this. There's the exploratory part, and then the whole thing needs to be scalable, it needs to be communicated, and security, provenance, and other concerns that actually make it applicable should be also a part of it. Provenance relates to, for instance, reproducibility quite a bit. And while doing that, how do we utilize the advanced cyber infrastructure, which is that green part in the right, which means compute storage network. At San Diego Supercomputer Center, we have expertise in both big data and high-performance computing systems. And we definitely know how to do that traditional application integration on top of these platforms. But the world is changing. Networks are changing. The Pacific Research Platforms is connecting its nodes in unprecedented speeds. And on top of that, on this network, we are now, through a NEEB grant from NSF, are able to put containers that can compute on the data through this network. So instead of transferring the data, you're actually docking a computing container to the network, and you should be able to do what you're doing. So that's a new way of thinking about it. And next steps would be adding all the rest of the capabilities on the clouds and up-and-coming architectures around this network that can compute on data. And now when I look at our solution architectures, it looks like this. Everything is composable. Network, storage, computation. They're all composable. And on top of it, through the Kubernetes or up-and-coming resource management frameworks, we can do dynamic coordination of resources. So if applications know what they need, Kubernetes can actually give that to the applications. And within those composable, on top of these, we can build data services that can take advantage of this framework and workflow systems on top that manage these data services and coordinate and do things with it. So that coordination is really cross-coordination across different platforms, something that we've done, which is a tool we developed over the years called Kepler, and we are iterating on that to make extensions for this dynamic behavior. So the idea is dynamic resource optimization and coordination, and then ability to explore and scale on multiple platforms, the combination of these two. And that's operations research at this point. We are really trying to understand how we can apply some of the operations research techniques to science, but without these networks, without those dynamic middleware frameworks that make those networks and container architectures available, like Kubernetes, we couldn't do this before. We thought about that, but it wasn't possible. Technology is coming together nicely. And we are using that. I don't expect anyone to understand it, but what's going on here is we are profiling the heck out of everything right now. And so we are trying to understand. So we can ask Kubernetes, what we want. We are really at that stage. And that requires data science too. We have to do time series analysis using neural networks and things like that to understand both infrastructure behavior and the behavior of the analytical methods on top of the infrastructure and the effects of data on those methods. We were funded by DOE and NSF to do that work. But it's not enough. We need to have domain knowledge built on top of that, because in the end we are trying to communicate a real solution architecture needs to come from the domain perspective. It needs to have the stakeholders, data sets, compliance requirements, actions to be defined based on those analytical methods, technical architecture, infrastructure, everything together. But bit of caution. I'm a big advocate for all these methods, but we really need to be careful. Right? Google Translate came up yesterday. It learns from our written and spoken language. So when I translate, there wasn't a linguist on the team when they built the Google Translate. Right? When I translate a doctor from Turkish, which doesn't have he or she concept, we have a genderless third person. It translates doctor into a he and a nurse into a she, right? Because it's learning our biases. And we are making societal decisions of who goes to jail, who goes to school, what school, based on these systems. And in science and medicine, things that relate to human lives and property. And it needs to be transparent and verifiable, accurate. Ethics is a big part of the data science education and training, in my opinion, and reproducibility and cost of these applications, because there's huge amounts of data or massive amounts of data, and exascale systems are actually able to maybe respond to some of the need in the new computational advances that are, or frameworks that are being generated. But there's a huge cost to it, both environmentally, energy costs, and financially. To summarize, I think my point was we need to build network data science as a collaborative entity. And it needs to be measurable, because we are trying to automate things without measuring. We don't know what we are going to be trusting. And in terms of networks, programmability and measurability needs to be a part of it. And I think PRP plus ChaseCI is a great example of that. And PPODs is our method. It's just one method to do this. But I hope we'll see more of these methodologies coming together to bring people together. Thank you.